So thank you for the introductions, and hello everyone. So I'll be talking about how to do data science and deep learning on Spark with 1/10 of the code. And the agenda of the talk is I'm going to be introducing our new product, Microsoft Machine Learning Library for Apache Spark. And we'll be talking about its vision, how it can help you as a data scientist to be more productive and use state-of-the-art algorithms such as deep learning or text analytics on scale. But before we get there, I would like to invite on stage one of our early users, Retik, who is going to be talking about snow leopard conservation and how the library is helping those efforts.
Thank you. So as mentioned, I do work at Microsoft, but I'm actually talking here today in another capacity. So I'm also the president of the board of directors of the Snow Leopard Trust. And we've been partnering with the Microsoft team on use cases in conservation. And so, as you might guess, the Snow Leopard Trust is dedicated to the preservation of snow leopards. And there snow leopards, some quick facts here, there's 4,000 to 6,000 of them in the wild. And they have a variety of threats. So they have direct threats like poaching, retribution killings if snow leopards kill livestock, and also kind of larger scale threats in loss of habitat, loss of prey due to loss of habitat as well. But the problem with conservation of snow leopards is that there's very little known about their ecology. So we don't know some of the basic things like their range, their movement patterns, and their survival rates. And so this really makes it hard to be effective in conservation because, number one, we can't measure ourselves to see if we're doing well, and we really don't have the data to go and do the type of influence that we need to do in conservation. And so to get a little more context, the snow leopards live in high altitude, 3,000 meters and above, and their range is in Asia and Central Asia. So you can think of high altitude places like the Gobi Desert, the Tibetan Plateau, the Himalayas in India and Nepal. And so if you know anything about sampling of animal populations, especially in something simple like birds, what will often happen is you send out a team of volunteers, they go count the number of birds they see, and then you do statistical modeling to get a population study. But that just doesn't work with snow leopards. And one of the reasons is they live in areas like this, very inaccessible, and they're kind of hard to find. This is a picture of a snow leopard. And there he is, right there, if you didn't see him. And so just the traditional method of going out and looking for them is not a feasible thing. And so what we've been doing at the Trust is camera trapping. And so a camera trap, as you might guess, it's that very large thing right there. It's very weather durable, can withstand impact, weather, what have you. And it does motion sensing photography for a couple weeks on end when they place the cameras out in areas that are known to have snow leopards. And so we've been doing this camera trapping for a long time, since 2009, and we have roughly 1.3 million images. And so when you look at the kind of images that you get in a camera trap, so on the top left, you'll see some pretty good ones of a snow leopard. But then on the bottom left, you see livestock, which we're not very interested in. And then on the bottom, you also see prey, which we do find interesting. But then on the top middle there, you actually see a picture of pretty much nothing. And so in the right conditions with wind and long enough blades of grass, you can get lots and lots of pictures that are fairly useless. And so, as a small nonprofit, we'd have to be manually classifying these images, and it takes hundreds of hours per survey. And so it's just not a feasible thing, but it was a perfect use case in image recognition to work with the Microsoft team. And so what we've been doing is doing image classification on the snow leopards. And so we're doing two things. In the short term, we're doing a binary, does a picture contain a snow leopard or not? But then with the ones that don't contain a snow leopard, we'd also like to move into, okay, there's their prey. And then in the ones they do, the harder thing is going to see, can we identify individual animals? And so once we do that, obviously the short-term benefits are fairly straightforward, right? We're saving thousands of researcher and volunteer time, and they can spend their time on actual conservation and science. And we're getting more and more accurate data on range and population. And so once we have this information, in long term, we can go and influence governments on where they put their protected ranges, negotiate things like whether mining rights should be given in a certain area, and just really gets us a lot more powerful in terms of influence, in terms of being able to actually do conservation and actually protect the snow leopard. And so we are a nonprofit, so how can you help? So we need more camera surveys. Since 2009, we've only done 1,700 square kilometers of a vast range. And in order to do the statistical modeling that we have, we really need a lot more studies, and that requires a lot more cameras. So for $500, you can buy a camera. For $5,000, you can fund a researcher. And honestly, any amount helps. So I went through this really quickly because we want to talk about technology here today. But if you are interested in learning more, you can contact me directly or check out our website at snowleopard.org. Okay. Thank you.
Okay. So thank you, Retik. So I'll be now talking about the library that was used in this work, the MMLSpark, and it's available as open source product at the GitHub. You can see Azure/MMLSpark. And actually, if you want to follow along and look at some of the examples while we go through and dig deep in the library, you can run this one-liner to grab the library from the Docker Hub and run it on your laptop. So if you've used Spark for doing machine learning or data science, you probably run into some challenges. So, well, the first challenge is that you often need to write lots of what I should call ceremonial code to prepare the features of your data for the machine learning algorithms. And by that I mean, for instance, coercing types and data layout to what's expected by the learner by using string indexing, type conversions, vector assembly. And what's even more complicated is that different learners have different conventions. So you end up with some amount of code that's not very modular or reusable. Say if you change your feature set or you change your learner, you may have to change that pre-processing code. Another problem is that there's a lack of domain-specific libraries that address certain important use cases, such as the image detection that we saw end-to-end for computer vision or for text analytics. And then there's limited capabilities for model evaluation and model management. So the vision of the Microsoft Machine Learning Library for Apache Spark is to enable you as a data scientist to solve machine learning problems dealing with large amounts of data. And we also want to make you, as a professional data scientist, more productive on Spark, so you can focus on machine learning problems, not software engineering problems. And we want to provide cutting-edge machine learning algorithms for Spark, for deep learning, computer vision, and text analytics. And our philosophy is to be open source. We want to make Spark better for everyone. And let's look at the quick example of using the MMLSpark library. An example is predicting income from US Census data. In a plain PySpark, you would read into data, then you would have to do lots of featurization and more features, and then you finally get to the machine learning part and get the results. But with MMLSpark, you simply tell which model you want to use, what you want to predict, and you pass the data to the model, and you get the prediction. And the train classifier that you see here takes care of the featurization of the data, coercing the data in the layout expected by the learner. And the design principles include being able to run on every platform and on language supported by Spark. We follow the Spark ML pipeline model for composability, so you can mix and match different pipeline components. We use data frames as the common format, and we provide consistent handling for different data types, including not just the basic types, but more complicated types, such as text, categoricals, or images for different algorithms. And now let me transition to Sudarshan, who is going to talk in a bit more depth about deep neural net featurization and the DNN capabilities of the library.
Great, thanks. So like Roope said, when we designed Microsoft Machine Learning for Spark, we wanted to meet Spark developers where they are. So part of what we did is to make sure that every library we built runs on any Spark cluster or on your local laptop or on the cloud or on premise, whether you're a Scala programmer using IntelliJ or a PySpark programmer using Jupyter Notebooks. We want to come to your cluster and bring our bits to you. Part of what we try to do in terms of providing functionality is to enable you to take a bunch of large number of images sitting in distributed storage somewhere and creating features out of them on which you can train lots of machine learning algorithms. One way to do it is you typically you can extract features from images using what are called pre-trained deep learning models. So if you have a scenario like with the Snow Leopard Foundation where you have lots and lots of images, but you don't want to train a neural net from scratch, what you can end up doing is sometimes take a very sophisticated deep neural net trained on tons of data by experts in the field and use some of the layers of the nets to extract features out of them. So for example, what you typically do is given a lot of a neural net, a deep neural net with lots of convolutional layers, chop some of them off the end, and take the output of the ones that remain as features. So doing this requires like knowing what model to choose for your application, figuring out how to distribute it efficiently among all the workers you have on your cluster, because some of these models can be humongous, and calling it efficiently, making sure you mini-batch it correctly, choose the right parameters, extract the correct layers, reshape your data, and so on and so forth. So what we did is we simplified all of that. So there's literally a few set of commands that you can run that will get a set of pre-trained models from a repository. You can search the repository for models that meet your use case. So if you're for example, doing classification on medical data, we have neural nets trained specifically for that. If you want to apply classification on scenery data, we have neural nets trained for that, which is what we used for the Snow Leopard Foundation. So it's very easy to discover models and to use them in the application of your choice. So as an example of how you might do featurization using DNNs using the MMLSpark library, what you end up doing is you first create a featurizer that we call CNTK model, because a lot of the underlying technology comes from this library called CNTK that's open source by Microsoft. You set the set of parameters telling the transformer where the inputs are, where the outputs should be. You go to the location of the model, which you get from our repository service, and then you customize the node from which you want to extract the features. Once you do that, you essentially feed this transformer a bunch of images that you've read in, and then you get the featurized images. As Roope explained, one of the things we did, one of the foundational pieces of our library is the assumption that everything we built should be compatible with Spark machine learning pipelines. So you can take the transformers that we have, intermix them with transformers that somebody else has built, intermix them with the estimators that come out of Spark pipeline, and then stitch it into one big composite workflow, and not only just train the model, but also save it and operationalize it. So we want to build the whole end-to-end experience, not just make just the deep learning part easy. We want to help you build solutions, not just the tools for them. So once you get the featurized images out of the deep learning library, you can use a regular vanilla Spark machine learning algorithm. You can use logistic regression in this case, or you can use gradient boosted trees, and then out comes a model that you can do predictions on. So one of the things we paid really a lot of attention to in our library is the fact that we want performance to be really good. So we want to give you ease of use, but without sacrificing performance. So as a result, what we did is we made sure that everything we built is directly on the Scala layer, goes against GNI, against a native library, and then we built in all the caching magic necessary. So if you have large models, they get downloaded only once. You mini-mesh the data, and you don't have to worry about constantly tuning your cluster, tuning your algorithm. You just give it, and we take care of all the rest of the stuff. So once you have the feature, so once people started using the featurizer, it immediately became obvious that we have a big problem at hand, which is how to get images into Spark, and that's a big open area for where people have come up with ad hoc solutions. So what we try to do is come up with a reasonable solution for how to comprehensively handle image recognition in Spark, which starts all the way from reading a bunch of images from stored in distributed storage, reading them in different formats, figuring out a way to get them in a shape that's most compatible with what the neural net expects. In a lot of deep learning applications, if you don't have enough data, you have to transform the images in various ways to generate synthetic examples. And doing that is very tedious. So we wanted to make things like all the surrounding aspects around dealing with images very easy for you and yet efficient. So to do that, we added a whole entire library just for dealing with images. So dealing with image ingress as well as a lot of image transformation. So let's take a look at that. So what we can do is, what we ended up doing is we built out this family of transformations built around OpenCV. So if you've done image processing ever in the past, OpenCV is one of the most standard industry-wide robust libraries for doing all aspects of computer vision. And so we exposed all the, or large fraction of the APIs and the capabilities of OpenCV as transformers and estimators in Spark. So you can intuitively do things like read images. So instead of, if you've use JSON files or CSV files, you say spark session.read JSON or read CSV. You can just as easily now say spark session.read images. And what we end up doing is we go to your distributed storage. It can be any distributed storage that Spark can access. It doesn't have to be just Azure. It can be HDFS, S3, you name it. It goes there, recursively traverses all the images, finds the ones that are in a format that it can recognize, and then just reads them into this highly efficient internal memory representation. The nice thing about this memory representation is that once the images are read in, you can push all the OpenCV transformations directly to it. You don't have to worry about moving data in and out. You don't have to worry about massaging data, figuring out whether it is RGB, HSV. All of that stuff is handled automatically for you. So, for example, what I can do is I can take my images that have been read from distributed storage. I can resize it. In this case, it's to 200 by 200, and then I can crop it to 180 by 180. And and we have a whole bunch of other transformations that are part of this pipeline. And so what you can do is once you run these transformations, you get a data frame with images. You can use them as all the operations that work on data frames work on these data frames with images. And there's very rich metadata and schema. So if you want to build your own UDFs on top of what we have provided, you're able to do that fairly easily. So we paid a high. We made sure that you can do that in a fairly straightforward way. And so once you do the image featurization and image lots of these image processing ones, our users started asking about more complicated stuff. So for example, that just does the transformation. So for example, they want to not just do a single binary classification like Ratik mentioned. We want to do multi-object detection. We want to rank all the images that we find. We want to use images as features to build a sentiment model, so to see if somebody is smiling or not based on their photograph or maybe some other feature that you extract from them. And so what we're doing is not just stopping with here, build a classification model and you're off on your own. We want to build turnkey solutions where literally all you have to do is give us a bunch of images, give us a abstract description of the problem, and we will do the rest. We'll do the rest. And the spirit in which we're building this extensions library is to have reasonable defaults, but then expose all the underlying guts for you. So you're able, if you're an advanced user, you're able to customize it. You're able to take what we have and then build on top of it and compose it with the rest of the Spark ML ecosystem. So that's as far as the image transformation stuff goes. Once you're more advanced, once you say, okay, I really have a lot of data. I want to really build a neural net from scratch. Can you give me the tools to do it? And so so what we did is also added the ability for you to train deep neural nets from scratch from Spark. And this is kind of interesting because to train deep neural nets, you typically need a machine or a cluster of machines with lots of GPUs that can churn through all the convolutions and the matrix multiplies efficiently. And that's not as easy to do with Spark. So what our users ended up doing was you run the pre-processing in Spark, you save the data, you spin up a GPU cluster, you move the data to the GPU cluster, you train the model, you move the model back to distributed storage, and then you operationalize. So we wanted to simplify all of that. So what we ended up doing is building a library or a set of functions in our library where you can spin up a set of GPU instances in parallel to your Spark cluster. So you submit your Spark job as usual to your Yarn master or to Mesos. You do all the pre-processing there, and then you tell it to train an estimator that in turn goes and trains a neural net. And what we now do is that we are able to spawn off the neural net training job alone to the set of GPU machines. And once the model is done training, it moves the trained model back to distributed storage where you can operationalize it as usual. So from the user's perspective, you're building a vanilla Spark ML pipeline, but behind the scenes, what it's doing is it's going off and training a bunch of deep neural net models on a bunch of GPUs. The other feature we built in, which our users explicitly asked for, is the fact that once you're done training the deep neural net model, you can turn off resources and you can deallocate them, so you're not getting charged for them, which is really important when you're in a cloud setting. So you can turn off the GPU instances, you can spin them back up only when you need to do the training part. But from the application's point of view, it looks like one complete pipeline. So that's on the training part. Like Roope said, stop by our GitHub repo and take a look and give it a spin. A couple of things that I wanted to talk about that's not just images but text is all the functionality we have added to easily operate on text. And so, like Roope said, real world data you have text, you have categoricals, you have things with missing values, you have integers of various precisions, and so we wanted to provide a simple set of turnkey featurization routines where you can just throw us a bunch of free-form text, set a few parameters which also happen to have reasonable default values, and then you get a bunch of features out on which you can train. And so right now we have a simple set of pre-processing and featurization algorithms available, but our hope is that over the next few months we will allow you to featurize text using state-of-the-art deep learning models, and that's coming very soon. So that's an example of how the text featurization pipeline works. You import a Spark ML pipeline. You import our text featurization transform. You instantiate it using the input and output columns. You tell it the kinds of algorithms to use, and out pops a transformer that you can build a pipeline out of. And then as you can see, it fits into the regular Spark ML paradigm where you can tune it, operationalize it, whatever. So that's as far as the text featurization capabilities that we built. There's more coming down the line, and please use our GitHub issues page to give us feedback and ask for features that you would like, and we're happy to build them for you. So like we said, we have a GitHub repo now. It's called MMLSpark on Azure. We have a very easy to try out way where you can just, if you have the Docker client on any platform, you can Docker on a single line, and you can try our notebooks. We also have recipes for getting set up on Databricks, recipes for getting set up on a local cluster, local Spark cluster using Spark packages, building from source, as a set of Maven endpoints where you can build using SBT and Scala and other, and you can also, and we're looking for, if you have suggestions on other platforms that we can publish or other recipes that we can publish, we're happy to take your input. So hope you'll give it a shot. And so Roope and I and a bunch of our team members will be at the Microsoft booth following this. So stop by, give us feedback, ask questions. Thank you.
Okay. Thank you.
Thank you. We have some time for questions. So if you want to please raise your hand, I can bring the mic to you. Or there you go.
Any thoughts about word-to-vec or continuous word encodings, not just in normal Wikipedia English, but jargon like medical, legal, financial?
Yes, exactly. That's a big user ask. A lot of our customers have asked for it, so we're definitely working on those in a few months, hopefully.
Okay.
Yeah, it's coming soon.
Okay.
Does this work only on Azure or?
No, any compatible Spark 2.1.1 installation on Python and Scala. And our bindings, we're working on them. So no excuse to try it out, like one of our colleagues says, yes.
Okay, so if you have longer questions or want to chat about your use case, like Sudarshan said, we'll be at the Microsoft booth, and you can find us there. So, thank you.
Thank you.
Thank you.